Hello there, Mr. Sutton here, bringing you the Algebra 2, Chapter 4, Quiz 2 Review Solutions on Polynomials Part 2. For this problem, they want us to solve for all of the complex roots. So let's first see if we can do this by factoring. Let's see here, we've got x to the fourth, second, and then a constant. Since the first exponent is twice the second one, and the last term is a constant, this is quadratic form. So we can try to factor this like a regular quadratic using x squared instead of x. So let's see here. Numbers that multiply to negative 42 and add up to 1 for this middle term. Well, 1 and 42 doesn't work. We've got 2 and 21 doesn't work. Let me think. 3 and 14 is no good. 4 doesn't work at all. 6 and 7, though. Positive 7 and negative 6, that would give us a positive 1. So I'm going to split this up then into x squared minus 6 and x squared plus 7. And now I'll just set each of these individually equal to 0 and solve them, probably by square rooting. So first thing, we can write x squared equals 6. And then if I square root both sides, I have x equals plus or minus radical 6. Don't forget the plus or minus there. Over here, we can write x squared equals negative 7. And then square rooting on this one, we have x equals plus or minus I radical 7. We can take out an I because of the negative there. And that's it. For this problem, they want us to write the possible rational roots of this function and then find all the complex roots. So for possible rational roots, we have plus or minus factors of the constant divided by plus or minus factors of the lead coefficient. So we've got plus or minus 1 and 2, because those are the factors of 2. Over, we need the factors of 6, so that would be 1, 2, 3, and 6. So now for the way that these evaluate here, we've got the numerator, all of those divided by 1. So 1 over 1 and 2 over 1, which is just 1 and 2. Next up, we've got the numerator over 2. We have 1 over 2, and 2 over 2 is just 1, which we don't need to write again. Then we have 1 over 3 and 2 over 3, so 1/3 and 2/3. And then finally, we have 1 over 6, and we could write 2 over 6, but that's really just 1/3, so no need to repeat that. All right, at this point, we're going to plug our possible rational roots into the polynomial using Desmos until we get a hit, get something that gives us a 0. So let's go to my Desmos calculator. And for this, I just need the scientific calculator. So let me write in f of x now. So that's 6x cubed plus 11x squared minus 3x minus 2. And I'm just going to start on the left side of the list and work my way over until something works. And because this is an odd polynomial, it's an odd power of 3 here, I'm guaranteed I'm going to get at least one real root. Hopefully it's a rational one as well. So we've got, let's try f of 1. That gives me 12, which is not 0, so let me keep going. Let me try negative 1 next. That's 6, no good. Let me try positive 2. That's 84, still no good. How about negative 2? Ah, there we go, that's 0. So I'll just write down what I got here. And I'm now going to use negative 2 with synthetic division to break this down a little further into a quadratic. Now I could keep plugging in rational roots and maybe I'll get lucky and I'll get the other two answers as well. So that is an option, but we're guaranteed to get the answer if we do the synthetic division path here. Whereas if I keep plugging in these rational roots, none of these might actually work. So let me do my coefficients. We have 6, 11, negative 3, and negative 2. And I'm plugging in negative 2 to all of this, so that's my k value there. Let me do my synthetic division line right here. And I'll just section off a little bit over here for the remainder when it gets there. I don't really need this little line, but why not? So bringing down my first coefficient, we've got 6 down here. Negative 2 times 6 is negative 12. Plus 11 is negative 1. Times negative 2 gives me positive 2. Plus negative 3 is negative 1. Times negative 2 is positive 2. Plus negative 2 is 0. Alright, so I have x plus 2, that's one of the factors. And I also have the quotient here, which is going to be 6x to the second power, because we started with third power and we broke this down once. So 6x squared minus 1x minus 1 All of that equals 0. And at this point I've got some options. So let me bring down my x plus 2 again. For the rest of this though, I could, if I wanted to, use quadratic formula on this and be guaranteed to get an answer, or I could try factoring it. Now let me think here. If I do the AC method on this, 6x squared times negative 1, that's negative 6. Are there numbers that multiply to negative 6 and add up to negative 1? There sure are. 2 and 3. So I actually don't need the full AC method. I can just do guess and check. I know that this negative 1, I'm going to need a positive and negative 1 to get that by multiplying. For 6x squared, I know that I'm probably going to need a 2x and a 3x if things are going to add up to a negative 1x here. The only other option would be 6x and x, and that's not going to give me a negative 1. So let me do 2x minus 1, and then the other factor would have to be 3x plus 1. Now this is just a guess. I don't know for sure that this is going to work. Let's double check it. 2x times 1 is 2x. Negative 1 times 3x is negative 3x. Negative 3x plus 2x gives us negative 1x. So that did work. Hey, I got lucky on my first try. Going through and zeroing these out now, we have x equals negative 2 for that first factor. For the next one, if I add 1 and divide by 2, I've got 1/2. And for the last one, subtracting 1 and dividing by 3 gives me negative 1/3. And if we just double check, 1/2 and negative 1/3, those are also on my possible roots list. For this problem, they want us to graph this transformation of f of x called g of x. So let's first describe what's going on here. We have a negative outside the x squared function. That's going to give us a vertical reflection. And then we have this plus 9 going on inside right here. So that's going to give us a horizontal, because it's inside, a horizontal shift, and it's going to be opposite of what we expect, so we're going left 9. So vertical reflection and translation left 9. Let's do our parent table of x to the 4th to start things off with here. I'm going to do everything from negative 2 to positive 2. So negative 2 to the 4th is 16, negative 1 to the 4th is 1, 0 to the 4th is 0, and then 1 and 2 to the 4th, we've got 1 and 16 again. For my g function, we're going to be switching things up a bit. So x, since we're translating left, we have to do x minus 9 as the new rule for x. And this vertical reflection means we have to multiply our y values by this negative 1 out here. So negative y is that rule. So let me do minus 9 to all my x values. Negative 2 becomes negative 11. Negative 1 is negative 10. Then we have negative 9, negative 8, and 2 becomes negative 7. For the y values, we just switch the sign of everything. So we now have negative 16, negative 1. 0 is still 0. We have negative 1 and negative 16. So I need to do some grid lines that will let me go from negative 11 to negative 7. So this is going to be a very left-shifted sort of setup here. And I also need to go from negative 16 to 0. So I'm thinking grid lines that go by like 2s or 4s, something like that. So I've got grid lines going by 2s, a whole lot of the left side of the xy axis showing here. And going through now, we have negative 11, negative 16, which is down here. Next up, we have negative 10, and negative 1 is right here. And then negative 9, 0 is right on the x-axis. Negative 8, 1 is here. Negative 7, negative 16 down here. And then let's just connect the dots with a nice quartic polynomial. For this problem, we're going to do some more graphing. This time around, we're not really doing a transformation. We're more using x-intercepts and also end behavior and maybe a few additional points. So for my x-intercepts, zeroing out each of these factors, we've got negative 2 for the first factor and negative 6 for the other one. And then for my end behavior, I've essentially got a positive times an x squared times an x. So that's going to come out to an x cubed, which is a positive x to an odd power. That type of end behavior is going to be line up. So we're starting below and ending above the x-axis when all is said and done. Now we need an additional point as well, a number between negative 2 and negative 6 to plug in here to get another y value. Let me use negative 4, and I'll do this on Desmos just so I don't mess it up. So let me just write in the f of x function here, and that's going to be 1/2 parentheses x plus 2 squared, and then we have x plus 6. Let me go down to another entry point, and I'll do f of -4, and that is coming out to positive 4. So that gives us the point -4, 4. All right, let's graph all this. So I have my first x-intercept of -6 back here. We have -4, 4, that's right up here. We have another x-intercept at -2, right here. And we said we were starting below the x-axis and ending above. And in between here, I'm going to have to go through this first x-intercept to get to this additional point I found. And I'm going to have to come down and then bounce if I want to be ending above the x-axis. There's no other way to get up here if I have to touch this x-intercept. And that's our graph. On this problem, we're trying to determine whether this function is even, odd, or neither. So the quick way to do this is, since this is a polynomial, we can look at the exponents and see if they're all even, all odd, or a mixture. Since this is a mixture and it's not all one or the other, that means this is going to be neither. If they were both even, it would be an even function. If they were both odd, it would be an odd function. There's also another way to do this by plugging -x in and getting h of -x and then doing -h of x. I'm actually going to show you that now. This is the more long-winded, rigorous way to prove it, but it's worth seeing. It's a good way to show work. So let's find h of -x. That's going to be all this stuff with -x plugged in. So that comes out to positive x to the 6 right here. And then this is going to be a negative since we're raising it to an odd power and it starts negative. So -3x to the 5th. To see if this is an even function, we have to compare h of -x and h of x. Since these two functions do not look to be the same, since they are not equal, that means this is not an even function. So that's how we prove it's not even. To prove whether or not it's odd, we also have to compare -h of x to h of -x. So what's -h of x? Well, that's all of this stuff negated with a negative distributed to it. So that's -x to the 6th minus 3x to the 5th. Comparing that with h of -x, they're close but a little bit different. This x to the 6th is negative down here. Since -h of x and h of -x also do not equal each other, that proves that this is not odd. Now, if these two had equaled each other, we would have said it was odd. If these two had equaled each other, we would have said it's even. Since it's neither of these, we write neither. On this one, we're trying to write a cubic function whose graph passes through these given points here. So basically, we're trying to get the equation of this graph that we see. The way to do this is we are going to write some factored intercept sort of factors, like x minus whatever the x-intercept is, and we'll put an a out in front, and then we'll plug in another point to find the a value. So going left to right, my first x-intercept is 0, so I could write x minus 0 for that factor, but I'm just going to write x, and I'll have that a to go with it right away here. So this is for the x-intercept of 0. Next, we need one for this 2, 0, so x minus 2 gives us that factor. And then we need a factor for the 5, so that would be x minus 5. This 1, 4 doesn't get its own factor because it's not an x-intercept. However, don't worry, 1, 4, we're going to use you too. This is the point we have to plug into what we've written here in order to solve for the a value. So I'm going to plug in the y value of 4 for this f of x, and I'm going to plug in the x value of 1 for these 3 x's I've written in here. And now once I simplify this and solve it, I'll get my a value. So we have 1 times -1 times -4. That's a grand total of 4 to go with my a. And then dividing by 4, we get a equals 1. Plugging 1 back into this formula we wrote with the a in it, this is just going to be an invisible 1 times x minus 2 times x minus 5. And this is a function that matches this graph. For this problem, we are trying to determine possible numbers of positive and negative real zeros along with imaginary zeros for this f of x function. A good place to start our journey would be by figuring out a total number of zeros just overall. positive, negative, imaginary, whatever. And we can do that by looking at the degree of our lead term here. So the degree of this polynomial is 4, so that tells us we have 4 total zeros. All right, now next thing I'm going to do is figure out total number of possible positive real zeros. So to do that, I just look to see how many sign changes are in the original polynomial. So we're going from positive to negative here, that's one sign change. Negative to positive gives me 2 sign changes for the f of x function. And the number of real zeros will be either this number of sign changes or less than this by an even number. So this is going to be either 2 positive real zeros or 0, because 0 is an even number less than 2. All right, so those are our 2 possibilities. Let's talk about negative real zeros now. To figure this out, I need to figure out the number of sign changes in f of negative x. So plug negative x into this function and kind of redo this analysis. So that's going to be negative x to the 4th minus 5 times negative x cubed plus 2. This first term becomes positive x to the 4th. And we have a negative times 3 negatives. That's an even number of negatives, so this becomes a positive 5x cubed. And we have that plus 2 along for the ride. In terms of sign changes, we're going from positive to positive to positive. So there are 0 sign changes. So that means we can say definitively, regardless of what's happening with our positive real zeros, this time around we have 0 negative real zeros. So to get our different possibilities and also figure out the imaginaries, we're going to set up a table. This table is going to have positive and negative reals along with imaginaries, and then we're going to pre-fill in this total column of 4. So one possibility I have is that I have 2 real positive zeros and 0 negatives. And if I've got 2 of positives and I have a total of 4 roots here, that means there must be 2 imaginaries left over. So this is one option: 2 reals, 2 positives, 0 negative reals, and 2 imaginaries. The other option is that we could have had 0 positive reals, and we still have 0 negative reals. That was guaranteed because of this. That means that there's room for 4 imaginary answers in that case. So this is our other option.